In nature, atoms rarely appear alone, but in many cases they are bonded together to other atoms to form molecules. And there is a certain rule or certain regulations on how these atoms can be bonded together. And this is the point of this presentation right now. Let's have a look at these Duplo Lego bricks over here, and some of these molecules, they're bonded together here. So these are atoms which form molecules. Some of these molecules do exist in nature, and others are not allowed, so they cannot exist. Let's have a look at this one over here. A blue Lego bricks that's oxygen. So we have oxygen over here, and over here, and these three oxygen atoms are bonded together over bonds, and the molecule over here has the chemical formula O3. I'm going to write this down here, O3, and that is ozone. So this molecule does exist, and this is possible. Every oxygen has two bonds. So you can see that from this oxygen over here, you have two bonds extending, and also from this one over here, and so on. So that is ozone. It does exist. And that's a possibility over here. Over here, these one over here, the green brick is carbon. And over here, the yellow ones, these are hydrogens. And the question is now, does this exist? The carbon over here has one bond, and this hydrogen over here has two bonds, one extending over here and the other one down here. And this is not possible. Carbon always must have four bonds, and hydrogen always must have one bond. So this molecule here does not exist. So let's fill this in the table already over here. The number of bonds that oxygen can have is 2. The number of bonds that carbon can have is 4. And hydrogen can only have one bond. And I'm also going to tell you the last one over here, nitrogen can have 3 bonds. It's possible for it to also have 4 bonds, but then there's a charge. That is chemistry, which is basically not part of this syllabus over here. But we just remember for our purposes, nitrogen has 3 bonds. So let's look at this one over here. Yellow is hydrogen. Is this possible? H and H, hydrogen over here, one bond. Each hydrogen has one line extending, one bond. This is possible. This is hydrogen gas, H2 gas, and yeah, pretty dangerous because it can explode. Over here, oxygen in the middle. Over here, a nitrogen and a nitrogen. Nitrogen must have 3 bonds. It doesn't work, so this one is also not going to be possible. Okay, so that is the purpose of understanding. Well, if you want to check if a molecule is possible, one of the first things I would do is I would check the number of bonds. So, and I would now like to also explain this using now a structural formula. And let's do the following over here. Let's say we have CH3COOH. And the question is this possible? By the way, this is acetate or acetic acid. This is the thing that makes vinegar sour. And it's a pretty important compound in organic chemistry. But let's see. Well, actually, I already told you that it's possible. I've given it away. But let's try to construct the structural formula over here. So the CH3 part over here would look like that. You have a carbon over here, that's this carbon. Then you have 1 hydrogen, 2 and 3. Hydrogen, hydrogen, hydrogen. So this carbon over here so far only has 3 bonds. So we need another one over here. It goes over here. And now we add the carbon over here. So this carbon is fine. The 3 hydrogens are fine. And OOH. And the question is now, how does this look like? COOH. And I'm going to show you the wrong way first. Okay, so this is wrong. COOH. This is wrong. Why is this wrong? Because this carbon now only has 2 bonds. So I got to erase this here. COOH is a very common functional group. It's the carboxylic acid group, and the COH actually looks like this. Here we have one of the oxygens, and over here we have another OH, the OH from over here. So, and that is now possible. This carbon over here has one bond over here, another one over here, and a double bond to the oxygen. This oxygen over here has two bonds, so that's fine. Remember, two bonds over here. Now, what about this oxygen down here? I only see one line going to the carbon. Where is the second one? We need a second one over here. Well, the second one I did not draw. The second one goes to the H over here. So this is a short way of writing it. If you do not like this, you can also write it like that. OH. Okay, so that is a second way of writing it. So this is a legal possibility. Now let's look at alcohol. So that's acetate, just in case you're wondering. Okay, or acetic acid. So actually, acetic acid is probably better because acetate is, yeah, forget it. It's we don't want to get into chemistry here now too much. So ethanol, which is the alcohol which can be found in alcoholic beverages, it looks like this. And that's it. And you're going to say, okay, why isn't there anything written over here? Well, if I don't write anything, then I'm implying that there is a hydrogen. So it's again a short way of writing it. So the chemical formula for this one is C2 H1, 2, 3, 4, 5, 6, H6, and 1 O. Some people do not like to write it like this. What they do instead, that's to indicate that it's an alcohol. You kind of want to keep the OH together in the formula. And some people write it like this, C2, H5, 1, 2, 3, 4, 5, and they write the OH separately. OH. That's also a way of writing it. And this way you are actually showing the reader that there is an OH group over here, which actually shows it's an alcohol. It's yeah, both is fine. I'm just saying this to make this clear. But in any case, I think the point that I tried to make is that you count the number of bonds. So if you see something like this over here, look at this, C2, C, and then over here a hydrogen, over here a hydrogen, over here a hydrogen, and hydrogen, then this does not exist because this carbon over here is 1, 2, 3, 4, 5 bonds. Does not exist. Okay, so always check the number of bonds first. And for nitrogen, okay, so that I also have this as a possibility, I'm going to give you an example with nitrogen. I'm going to draw you an amino acid, and the formula for this, or the structural formula for this, you have to know anyway. Amino acid. So, and it looks like this. I have a carbon over here. I have a rest, an R group, which could be anything, hydrogen or another carbon. Over here I have a COOH. This looks familiar, right? So we have it from over here as well. And over here, down here, we have a hydrogen. And over here we have a nitrogen. That's the thing that I wanted to make clear. And a hydrogen over here and a hydrogen over here. And you can see that this nitrogen over here has 1, 2, 3 bonds. Okay, so that's an amino acid. And don't let the R confuse you. I'm going to explain this more in a different video. The R is a rest, and it's basically is a placeholder for another element. So let's move on to the next foil. Oh, okay. Here's the text. Which ones are correct and which ones are wrong? I already answered this for you. Okay, so let's move on to the next one. Bonding. We talk about the different types of bonds now, and the one type of bond that I mentioned over here, all of these lines over here are so-called covalent bonds. They're pretty strong. They're strong bonds, but there are other bonds as well. So matter and energy are conserved during chemical reactions. New bonds are formed, and what are they? They're the covalent bonds, the strong ones. They're the hydrogen bonds, and they're the so-called van der Waals bonds. And this is a quick overview that I want to give. But the really important thing is there's conservation. What does this mean? If I have a chemical reaction, I cannot make or destroy matter, atoms, and I cannot make or destroy energy. And in order to illustrate this, I've used again my Lego bricks over here. And this one is ethanol, this is carbon. We just talked about that, carbon. I have my 3 hydrogens over here, 1, 2, and the other one is down here. It's a little bit hidden. And over here I have 2 hydrogens over here, and I have my OH over here. So this is ethanol, or ethyl alcohol, which is alcohol. And I want to burn this. And what I need is an oxygen. I have oxygen over here, double bonded, so it's O2. It's molecular oxygen. I have oxygen over here as well and over here as well. And I basically react it, I burn it, and what do I get? I have over here my carbons, carbon, oxygen, oxygen, so that is CO2. And what I have over here is water, oxygen, hydrogen, hydrogen, which is H2O. So by burning it, I get 2 carbon dioxides and I make 3 molecules of water, 1, 2, 3. But the real point that I want to make is I did not make or destroy any of these Lego bricks, any of these elements over here. So if I'm starting off with 1, 2, 3, 4, 5, 6 hydrogens over here, at the end I also have 6 hydrogens over here. Over here I have 1, 2, 3, 4, 5, 6, 7 oxygens. And I have 1, 2, 3, 4, 5, 6, 7 oxygens over here, 2 carbons over here, and 2 carbons over here. So I have not made or destroyed any of these elements, and that's kind of important. In the process, I'm releasing energy as well. Energy which was stored in the bonds here, so it's also converted to heat. So that's why you can burn alcohol. And all of these lines here, these are covalent bonds, and the covalent bonds are there when electrons are shared. And I'm just going to write this like this: E minus electrons. It's my way of writing electron are shared between atoms. So electrons that, for example, let's hold the water together over here. The oxygens are here flying around the hydrogens and flying around the oxygen and the hydrogen, so it's shared. There's another type of bond which is a little bit weaker than the covalent bond, and these are hydrogen bonds, and they basically also happen, well, if I explain it in a simplified way, because of attraction between molecules. So hydrogen bonds occur between hydrogens and oxygen atoms, and how this works is basically explained later in a different video. But what you should know for right now is that it's a different type of bond and they're much weaker. So different water molecules are attracted by hydrogen bonds. Just to illustrate this, I have a water molecule over here. It has 2 hydrogens. There's an angle between here. And if I have another water molecule over here, H2O, then between the oxygen over here and the hydrogen over here, there is an attraction. And I'm going to make a dotted line. So there is a bond, but this bond can break and reform easily, and this is why water is weaker. And the van der Waals bonds, they're really weak. They're really weak. In biology, we're not going to talk a lot about these, but basically they hold oil together. Some molecules do not form hydrogen bonds, but oil is still liquid, and how is this held together? It's by van der Waals bonds or van der Waals forces. And they are very common, or more common in molecules which are non-polar, which do not carry a charge. So, for example, in e.g. oils. I'm just including this. Maybe some of you also have chemistry, and just to give you an overall completion for biology, these two are really important. Okay, and hydrogen bonds are going to be reappearing over and over again in the biology syllabus. Okay, so this was basically the chapter on bonding. Please remember that chemical bonds are important to form molecules.